Thanks a lot, Ihor. And so I know I am the only one between you and lunch, so I'll try to be as quick and as entertaining as I can, so that you don't have the, your stomach doesn't distract you too much. So yeah, thank you everyone for being here. And I would like to talk to you today about how to scale some Spark applications in the future. And then we can, I hope it's mostly inspirational, and then we can see whether this is the future we want, and whether this is a future that we want in the close, or is something a bit more in the long term. So I am software engineer at Databricks, and I think I was the user number 2 of Spark. That was really a long time ago. And I've been working on a number of packages around Spark, and also on a number of libraries around Spark. So you heard about Databricks today, and but today's talk is not necessarily about directly about Databricks and about Apache Spark. It is going to be more about some personal ideas about what Spark could look like. So Spark 2.2 is currently being released. We are having some release candidates. Spark 2.3 is being thought about. So really, I think at this point, it's time to think about Spark 3. And this presentation is going to be some ideas which I've been sharing with some of the lead developers of Spark for a few years now, and that finally had some time to put together. So and, I hope that we'll have, at the end, a good conversation about where these ideas can lead. So I'm a statistician, and I'm a fairly theoretical guy, but I think theory actually can be useful. And I really like this quote from the founding father of electromagnetism, which there's nothing more practical than a good theory. So as we consider Spark application these days, now that Spark is becoming popular, we need to ask ourselves the question, what kind of challenges are going to lie ahead as people use Spark and deploy Spark in their environments? And also, because I really like theory, and I think because theory can inform us into building some practical frameworks, what kind of good foundations we can find to build big data applications? So even though I say I'm a theory person, I'm only a statistical theory person, and I'm not a programming language theory person. So if you come to me to ask me, is Spark an applicative functor, or is it a functor, or even is Spark a monad, then I will not be able to answer you, and I will probably run away. But nevertheless, I think there's a lot of interesting thought that we can have from the programming language community. And even though I'm going to use some programming languages here that some people may not be considered as mainstream, like Haskell, I would like to emphasize the fact that everything that is going to be discussed here really can be implemented in any modern programming language, be it Python, Java, Scala, C++. So don't feel afraid by the code that you're going to see in some of the examples here. So I'll talk first about how Spark is being used these days, what we can do to fight some of the issues that we can see and that we can foresee for Spark, and then I would like to share with you some prototypes that could inform us onto future direction of Spark. So when people think about pipelines for doing big data, usually they think about something like this, where you have, and this is also how you draw it usually. You have one input, you have one output, you have a couple of queries that you plug onto it, you have a couple of databases that you plug onto your system, and that's about it. That's really what we would like to imagine how the world is like. But really, what it's looking like right now is more complicated already. You have usually multiple steps. You have all these steps that start to interconnect with each other, and it's getting more and more complex. And what we would like to refuse to see, but what is really approaching very rapidly nowadays, is something that looks more not even like a pipeline anymore, but more like a refinery, where you have hundreds or thousands of inputs coming in, hundreds or thousands of outputs and queries that you want to plug into the system. And usually you want to be able to mix interactive batch queries together and also do, for example, streaming on top of that. So as we see this future coming in, now we need to ask ourselves the question, how does Spark support this kind of future workloads, and how can we enable that to make it more easy and also more scalable for the users? So as I was mentioning, when you think about data pipelines, I think it is a very bad idea because it gives you the illusion of simplicity. You really think one input and one output. And already if you look at all the all the big data systems that exist, they already work really like a tree where you can combine multiple inputs and usually produce one output. This is essentially what the SQL allows you to do. You can combine multiple sources, you can join them, you can do other transform, and then you get one output. And this is essentially what Spark lets you do. But what the user really wants more and more is multiple inputs, multiple outputs, and essentially we have to forget about trees. We need to think about directed acyclic graphs, so the DAG paradigms. And and in order to enable that, we also need to think of data processing becoming not just one element, but since we combine all these elements, we need to think about it as a complex system. And you could say, OK, this is something that is already done. You can already use some existing tools like that, for example, like Airflow, or FB Learner, or Luigi to combine all your pipeline elements together. And these are very general schedulers. So this is what people use in practice. And it's successfully deployed at large companies. But these are general tools. They allow you essentially to run something, hope for the best, or sometimes they even let you figure out if you have an issue, some sort of issue, and then be able to do something with it. But they lack the notion of understanding what the format and the schema of the input is and what the output is, and let you understand and combine these elements together and being able to reflect on what is happening in the system. Essentially here, we're separating scheduling and the actual transform. And I'd like to explore how we can combine that again inside Spark. So if I'm thinking about what my ideal big data system should be like, here are the characteristics that I would like to see in the system. The first one, of course, is scalability, because we're talking about big data. And by scalability, I mean not only scalability in quantity, so how big the data is, but also in terms of diversity. So how many sources and what kind of sources I can combine inside the system. So that's the primary characteristic I would like the system to have. The other one is chaining, which is how we can express, if we have a transform, how we can combine these transforms one after the other, and also having all the logical relationships between the transform, knowing that if I have employees coming in, then I'm going to have employees flowing out into the next step. The other one is composition, which is pretty hard to achieve right now in big data systems, which is if you have some teams assembling smaller blocks that let you transform some data, how can you build larger applications out of that while hiding all the low-level details of these individual blocks? And finally, this is more for developers, but I think it's absolutely crucial in practice, is determinism, which is if you have an input, you would like always to have an output that is well-defined. You would prefer not to have something that will depend on the weather outside the data center, or whether the electrical plug electric current was following certain patterns when you were doing it. You don't want to be following what the whims of the random number generator. And being able to have deterministic output lets you do a lot of optimizations after that, as we will see. So how is Spark doing so far? Well, I would say that all these steps, you can do it, except maybe the determinism, but it is really hard to do. And especially, it is really painful for the programmer in some respects. So for example, if you have this small program, which we don't need really to understand exactly, but except to see that it is taking some data in, you are doing some caching because you want to reuse the same data set. You're going to do a few transforms after that on this data set, and then you're going to write the output. And it could take a few hours to do each of the steps. So this is a typical job that you would see for doing ETL transform. And for example, here, I did a typo. Add ID, there's 2 Ds here. But I would only notice that after a few hours. And then once I solved that, well, I forgot, for example, that the output directory was not created in the output system. So I have to redo it again. And in the process, after doing a few iterations, since I kept caching and caching my data, well, eventually I will maybe run out of disk. So this is all these kind of issues that I would hope the system would take care of for me. And really, so the kind of issue that I would like to get rid from my data systems go down, I would say, to these four issues here. Ego evaluations, missing input to output, resource leaks, because that's something you should be able to take care of, and also schema mismatch, typing mismatch, being able to know what comes in and what comes out. And so let's see how we can deal with that. So if we think about it in a bit more of abstract terms, here is how we could think of a data system. You could think of a data set as being a collection of elements, all of the same types. This collection could be very large, very small, infinite maybe. You don't know, but it's mostly you want to associate a type to it. And then one idea that you can have about it is that this data set, you can never actually get elements directly out of it. You can never really poke the content inside, but you can make some queries out of it. And outside the query, you get not necessarily directly a result, but you get an observable, a box that will contain your result, which would correspond, for example, to a data frame with a single row. And in Scala, you could represent it by this type. So let's take an example with this data set of, let's say, all the employees or ex-employees of the US federal government, which is a big data set. There are a lot of employees. And let's say that we have their pictures, we have their names, we have the size of their hands. And one thing that we could do is, for example, we could observe how many elements there are. So for example, here I have 3 elements. We could observe the largest hand out of this data set. So that's one thing that we can do. We can transform this data set. The other operation that we can do is transform this data set. So that would correspond to map or group by operations. So we see, these employees definitely got transformed into some other states here. And we'll see how long it will stay this way. So these are really the two operations you can do on the data set at a high level. And one principle that you can do here is when you do these observations, the result of the observation should not depend on the layout of the data or the ordering of the data. So in that case, you can never observe how it is partitioned, how the elements are stored, and so on, which is something that right now Spark actually exposes to you, and which is crucial for some operation of Spark. And it has some mathematical consequence to say that we cannot observe that. One of which is that all the operation that you can do follow some very precise mathematical formula, which is here the monoid structure. And it gives us, after that, a lot of power coming from algebraic formulations. And we'll see that a bit later. So the last principle I would like the system to have is to say that that everything that happens when you read or write, or when you observe some things, is always observed within this system, which is what I call the closed world assumption. So you can model all the side effects, such as reading, writing, inside the system, and you can track them down. So as we'll see, this will allow us to do some pretty good checks about reading, writing, and also caching that are right now beyond the scope of what Spark could do. So to make it a bit more concrete, here is a couple of operations that we can do. So a data set, for example, here could be a data set of integers in Scala notation, and the maximum, for example, over this data set would not return the value. It would simply return an observable, so a black box, that then we can query later. The union takes 2 data sets, return data set, that's what you would expect, and collect, unlike the current Spark API, would return to you an observable of a list. So you would not get directly the list. You would get this intermediate step that then you can compose in some other ways. I'm going to make that more concrete with some examples. So I have built an implementation of this principle inside as a program that I call CARPS. And this implementation tries to implement these principles on top of Spark by building essentially a Haskell domain-specific language on top of Spark to implement that. And it works by letting the user write some queries in something that looks like what you would do with data frames and data sets. But instead of running it directly onto Spark, it first builds a logical plan of all the operations that you can do, and then asks Spark to execute these. And it tries hard to maximize the developer happiness, I would say, by trying to, before even it touches the data, it tries to it tries to find as many mistakes as it can, which is very fast because it is in the front end in Haskell, before even it starts to run the computations. And because it can do all these correctness checks because of the lazy nature of the program. In that case, since it knows all your computation before you even start, even before it starts to run them, it will be able to check that everything is properly typed or had the proper schema and so on. And you can also use that as a global optimizer for your pipeline. And we'll see some short examples for that. So let me show you what it looks like in practice. So I have here, yes. So I have here a notebook which is written in Haskell. And I can, like I would do in Python or in Scala, I can load some imports. And I can start by defining a data set here. So this data set is built over a list of elements, and they are all of type integers. So that's something that you would do, for example, this is something you would expect from Scala or Python. And if I try to, for example, count the number of elements I have inside, it is not going to return to me the result immediately. It is simply going to tell me, this is the result, and it's going to be of type integer, and it's not, and you can query it later. So the nice thing about this lazy model is that then you can continue to do other operations on it. For example, I could do some other operations here, and I could take my count, and I can do some further manipulations over it. And because I'm building a graph of computations, one of the nice features of doing that is that then I can introspect the full graph of computations, and I can ask the program to show it to me. So here I am using the tensor board representation that comes from TensorFlow. And this corresponds to the graph of all the operations I am doing in this small program here. So my last element, x, is going to be the top one here. And I can check that it is of type integer. And I can see that it depends on one constant and on the count operation that I was doing before. And this is before I am running everything. So if I want to get the result, I can create a Spark. So I can talk to a Spark context. Oh, yes, it already exists. And I have behind the scenes here a Spark context, a Spark implementation running with a small plugin that accepts these kind of programs. So now I can launch the computation to actually retrieve the results. And behind the scene, it is talking to Spark. It is launching some data frame computations. And finally, it is returning to me the count of the elements. So this kind of API separates completely how you would describe your operations to how you would run them afterwards. So this is the part where I would describe the operations, and then eventually I can decide when really I need them, how I can run them. So some people told me this is useless, because of course Spark can already do all of that. What is the point in having all this further complexity over that? It turns out that most of the operation that you see in Spark can be implemented in terms of a few small primitives, such as mapping over the data, grouping by, collecting, and so on. And with this kind of system, you can do, and because we have strong algebraic laws over it, because the operation follows some very specific structure, it turned out that you can rewrite a lot of the programs like a compiler or a database interpreter would do, but at a much larger scale than what Spark could do. Because Spark, when you do, for example, a collect operation, will be forced to directly give you the result. Here, since we delay all the production of the result until the last minute, we can check and we can optimize many more things in the process. And on top of that, we can also add some hints to the SQL optimizer to be able to optimize further the program. So the big question for most of these systems is, of course, how you deal with getting data in and writing data out. And one assumption which is made here is that the only type of effects that you can do is just reading and writing these data sets. You cannot, everything else is not considered from the system. Printing is not considered. And also, one thing which is interesting is that when you write, that can be considered as an operation that you observe. And since the operations are all deterministic, and since you can cache the results, then you can force yourself to only recompute data when the data changes. So here is what it would look like. So let's say that here I have, So let's say that I have a small data set here that contains information in JSON about employees. So, for example, salaries and the name of people. So I can ask Spark to infer the schema of the JSON, and it tells me, okay, there's a name which may be nullable, and there is a salary which may be nullable. And I can then collect this result. And so that would be the operation that would happen behind the scenes. I would load the data using the generic data source from Spark, and then I would collect the results. So this code here, which is pretty ugly, but it shows you the operations that are being done under the hood. If it wants to show, yes. So behind the scene, this program is going to check that is going to check the timestamp of the input to make sure that when it starts the computation, maybe it has seen already the computations. And when we run so I can run the computation, get the results, and behind the scenes, the system can cache the result because it knows the input, it knows the timestamp of the input, the source of the input. It can, and then it knows that the output is going to correspond to this row here, and it knows that in between all the computations are deterministic. So if I were to rerun these computations, then it would actually not recompute anything. It would give me a placeholder that corresponds to the result I just computed. So if I were to rerun the same computation here, it would directly give me the result without running anything in Spark, because it knows everything is deterministic, and it knows the file that was being read hasn't changed. So you can imagine how you can combine that at a much larger scale, and how you can prune out a lot of very complex computations without the user being involved in the process to do that. So yeah, so what happened behind the scenes is that it started from this data set here. It computed some timestamp and some hashes between the elements. And since it is all deterministic, all these hashes are unique for the given timestamp of the file and given the name of the file here. You can then run some arbitrary computations around. And if the file happens to, and then if the computation happens to be the same, then you can simply plug the existing results onto the final computation. There's no need to recompute a large parts of your compute graph this way. So how about scaling in terms of composition? Well, one thing that is pretty interesting with this kind of system is that if you have very large graph of computations, for example, if you define functions that, for example, compute the mean, and then compute the centered value, so where you subtract the mean and then you scale it by the standard deviation. You can associate also names to each of the operations, and since it is all lazy, you can compute a graph of all the operations that you're going to do. So Spark will not be able to do that because whenever you would want to compute, for example, the mean of your data set, it would have to stop the computation, compute the mean, and then return that to you. But here, since we are delaying all the operations, we can compute fairly complex graph and then introspect them to see what is happening. And you can see already how under the hood, even though we didn't ask this program, even though this program reuses actually the mean of the data several times to compute the standard deviation and the final output, it is able to share already some elements between different places of the graph. And this is not something that, as a programmer, I even need to do. It's simply because it knows that the computation are deterministic, so it can reuse the same path across the system here. And if you have been using the Spark UI to figure out what your job is doing when you run some computations, it is pretty typical to arrive and look at the graph output and think, okay, I have here this map partition RDD something. What does it correspond to in my graph in my computations? So with this kind of system, since here you can associate some names to the logical operations, you can also when you run the computations, you can also associate these high-level names to which operations are being done under the hood by Spark. And when I run the computations over there, I can then plot back the RDDs that correspond to each of these computations, all with the logical dependencies between each of the elements, which is something that Spark cannot give you really right now. So for example, if I wanted to compute the mean here, I can see that I have this particular RDD operation that happened here, and then I can trace it down precisely to the fact that it was computing the mean, and I can check after that how it was being used in the centering, and how all the operation flowed across the system. And this kind of overall global idea of what your program is doing when you run Spark is something that is really easy to do once you have access to the full graph of computations. And one cool detail here is that even though it started from the same data set, it figured out that it could compute in parallel the sum and the count, for example, to then divide them together by the mean. Of course, Spark has some optimized version for doing that. But in that case, it can automatically figure out when to run some computation in parallel until it needs to join them together for dependencies. OK, so as future directions, this is still, of course, fairly primitive. It doesn't allow you to do that. But it's mostly to show the kind of potential we could do if we wanted to change a bit some of the APIs of Spark. And one thing which I look forward to is having a Python interface to make it a bit more approachable, and also finishing some of the group by operations, which would allow us also a lot of very cool optimizations under the hood. And finally, for SQL, it's also very easy to add SQL parsing in this kind of system to understand what is happening between the different elements. So even beyond this prototype, I would like us to think about what we think data processing is going to look like probably in 1 year, 2 years, 5 years. I think it's going to be mostly about managing very complex data flows. And the functional world has been dealing a lot with this kind of issue before. Spark provides some really strong foundations as an operating platform for doing this kind of very large data manipulations. And having more lazy, more declarative APIs would alleviate a lot of the complexity that people have for this kind of operations. So you can try this out. This code is all on GitHub, and you can also there's a Spark package that corresponds to the server part written in Scala to plug inside Spark. So a lot of things also correspond. I learned from reading this advanced draft of this book. So it is available as well online. I would recommend to check it out. OK, thank you for your attention. And I think we have a few minutes for questions.